Okay. Right. What's I doing? Okay, right. Yeah, so it's been a while since I have decided to do my whole Connect 4, stream. I have a lot of catching up to do. So what did I do last time? Let's look here. Connect 4. Well, let's just see where I left off. 9 commits. Last commit was 2 weeks ago when I last streamed. Initial playable game against bot making random moves. Right, this is like a bundling function. Okay, very tiny commit. Not much, and then here's the game. I'll go first. Bot's making random moves, good. Let's just try a cheapo. Yep, let's just win horizontally. Game over, you won. Alright, now let me just kind of win diagonally. Okay, I should be careful. This bot is putting me to the test. Oh wow, it blocked it, okay. Well, actually, what if I can let the bot win? Game over, you won. Oh, right, because I won horizontally. Oops, I want to let the bot win. I want to see if I can get the bot to win. Come on, bot, you can do it. Game over, the bot won. The bot won horizontally. Okay, now I'll try to win diagonally. I know I already did this, but I just want to do it again. Game over, you won, because I won diagonally. Okay, good. Okay, so where was I? I know I see a bunch of TensorFlow.js stuff. Actually, what's this? Oh, right, I was looking at some math. Wait, what? How do I bring those notes there? What? So I have desktop, Firefox, preview, and then notes, right? Oh, it's that spinny icon. It's that spinny icon that's going on. It's just like lagged. It's not responding. But anyways, Connect 4 detour. I'm reading these numbers here. Initial base game logic. I think I'm done with that. Actually make a website to play against the bot. Bot can initially make random moves. Okay, so as of the last stream, I believe I completed that. And then now we're on the fun stuff. Architect a neural network for C4 bot. Create some Monte Carlo stuff to implement Monte Carlo tree search ideas to be generic in nature so we can swap out the C4 code and use BumperCoin specific code instead. Train the bot. Okay, so 1 and 2 are done. And then I started looking at TensorFlow.js because like BumperCoins is I made it in TypeScript, so it's JavaScript. So like once I create bot for it, like I wanted to reuse the same game code, like the same physics game state code, so that like to keep it in the same language, to keep it in the family. Right. So like, okay, the lag stopped. Wait, what? Nope, back to spinny color wheel thing. Anyways, 1 and 2 are done, and then 3, 4, 5, which are the hard stuff. Well, 1 and 2 are the boring scaffolding stuff, so I guess it's time to actually like work on the bot. Okay, so let's actually look at the terminal. Let's So what's this? Right, there's like this whole node backend, like to use the GPU, I think. Is this a get repo, get status? Okay, so there's a lot of stuff. So let's look at our diff. Okay, yeah, that sounds good. Get add the dot get ignore. Get status, so then package lock package. Yeah, let's just see what this package is, just to refresh my thing. Okay, so we have tf. I think we actually only need to have this dependency, but I'll just leave those two in there. Why not? Okay, yeah, that sounds good. Get add package, whatever those are, all of them. Get status. Okay, so test.html, test.ts. You cannot open application notes because it's not responding. Oh, that sucks. Let's just force quit it, right? Let's just, how do I quit? Command Q, right? Okay, it's being really dumb. Let's go to the desktop. Then let me just right click it and then force quit. The application notes cannot be opened. Well, why is it open? What? I just quit you. Okay, so it's quit. Anyways, right. So back to terminal. What is our test.html? Okay, so then here's just this test where I basically just like I got 8.27. So what is this doing? It's basically it's creating a sequential model. It's adding some layers. So basically defining a model here, and model.fit is to train it, and then model.predict is to actually like make the inference, the prediction, like to actually invoke the neural network on this input tensor. Okay, so then right. So after we fit it, after we do the training, we like do this callback stuff. And this is test.html. So I believe that's actually open somewhere. One of these tabs. Let's duplicate this. And test.html, right? Yep, it's already there. Open console to see results. 8.963. Refresh it. 8.947. 8.9. So it's basically almost 9. I think I remember that right there. So like when this is doing like .print, like that's what's actually printing it out open to see the output. Okay, that looks good. Right, the 4x1. Okay, so then that's like that's like a very simple neural network. Where's my whiteboard? Board does not exist. Well, I see it. Anyways, yeah, it's just like this thing right here, which I'm hovering around. Like that's like the input for this very simplistic model we have here. And now what I need to do is to actually create a neural network for Connect 4 and then BumperCoins. I know I've talked about this in previous streams. Let's drink some water. Okay. So then what? Like, what am I doing now? Let's refresh this. Maybe get a new whiteboard by clicking accept cookies, cookie settings, Strictly necessary. Confirm choices. Okay, so then now we need to create a convolutional network. There'll be of connect 4, right? Just connect 4 neural network. Well, no need to write that out. So we'll have 2 image stacks, right? And then these will be like current player, like cur player, the player whose turn it is, like cur, and then the other, like the next player who's like the waiting player. So like that will be kind of like it's like if we have like this thing at like row I column J, if you have like this thing turned on, it'll be like a binary zeros and ones IJ. Then like that would correspond to like in this I and like in that J, you would like that means that they have like a coin placed there. And then similarly, like same for the other player. Right, so then connect 4, what is the picture of it again? 1, 2, 3, 4, 5, 6 rows and 7 columns. So R equals 6. And then this thing here, C equals 7, where R and C are number of rows and columns respectively. Okay, so then like, so our input size is going to be two planes. Like it'll be, so our channel size, our channel would be 2. Like in image recognition, whatever, you have like 3 for RGB channels. This time the channel will be like 2. And then like the actual images here would be like 6 and then 7. So I think like the dimensions would be like 2 by 6 by 7, where this is the channels, that's the row, and then that's the columns. At least that's what I'm thinking. Okay, so yeah, let's define a model then. TensorFlow.js examples. What is this? Tensor. Okay, why am I looking at Tensor? What is this supposed to be? Let's see my history here. Getting started with Tensor. That looks like a good link. What is the sense tutorials? Set up Tensor reply. Well, I already got one set up, so I kind of know that. Let's close this. What is this? Yeah, we did that already. Example, let's close this window. Whiteboard, leave that open. What is this is the GPU stuff. We got that sorted out. Close that. This is a crucial article. First of all, I want to just like implement this whole neural network, and only once we do that, we'll look at this Monte Carlo tree search. I mean, I know I've definitely read this like many times by now, both like on stream and like also like off stream, and like several years ago. So like this like can probably like write off a memory at this point. But anyways, the point is like right now I'm just gonna focus on neural network for Connect 4. And I know I've talked about how to like, it'll be the same thing for BumperCoins. I did a whole stream where I talked about input-output differences in BumperCoins and Connect 4 and why Connect 4 is like super simple compared to BumperCoins because like huge branching factor. But like at heart, like it's the same idea, image planes, right? Except like the policy vector, the policy output, and the policy output, like this thing right here, is like super complex for BumperCoins because of the pass action and like because of like you have like different like planes, right? Like the policy is kind of like, I mean, I already talked about it earlier, so like there's no point I mean, I could recap it a bit, but basically like we can kind of view the policy if we have no passes and like if they have to make a move, then like the policy would be like kind of, we can visualize it not just as like a flat vector, but we can actually visualize it in 3D where like there are a bunch of image planes where like each image plane, like the first image plane means like launch it with an angle theta is of 0. And let's say there's 6 planes for like 0 and then like whatever pi over, so 2 pi is 360, that's full, and then 6. So 2 pi divided by 6 is pi over 3. So it's like we have like, so whiteboard, right? So we have like 0, like pi equals 0, and then we have like this whole like kind of all the directions we can launch a coin. Like we're discretizing our world into like 3, right? So it's like that. So it'll be like pi over 3 radians, and like that'll be 2 pi over 3 radians, and 3 pi over 3, which is just pi, and so forth, dot dot dot, all the way to what is this? What is 2 pi? What is 6? So it'll be 5 pi over 3, I think. 5 pi over 3, and that would be 4 pi. Wait, no. Why can't I do math? So that's pi over 3, 2 pi over 3, 3 pi over 3, 4 pi over 3. 4 pi over 3 over 3, and like these are all the angles. So like each like the policy vector would be like 6 image planes, like just a stack of like 6, where like the ith plane would correspond to like which angle you're launching the coin. Was it 6 or 12? I forgot. I think I was thinking of 12, but like we're like it was gonna be 12 because like you'd have 6, but you'd have like kind of some percent and like some percent, like different different magnitudes of flicking the coins. But anyways, this whole thing is irrelevant for Connect 4. The point is it's gonna be quite difficult. Like there'll be lots of like extra numbers and like a more complex design for BumperCoins, but like they're still the same thing. I have some like I think I spit on my screen. Okay, let me just clean my computer screen. Oh, right. Sorry about that. Or maybe it was there from before because it's kind of like not going. Right. Anyways, yeah. Okay, so then right now let's look at this example neural network. There's a neural network that is parameterized. Okay, 2 outputs, a continuous value of board. So we can't use a sequential model. We have to use like the functional. Like we need to like it can't just be like a sequential. We need to like split out for the 2 output heads. A continuous value of board state, and then from perspective current player. Yeah, current player perspective, like the current player. That's kind of what I was writing. The policy is a probability vector of all possible actions. So in this case, it would be the policy which we return would be like the size of like 7, right? Because like you can drop in any of the 7 columns. Whereas for a bumper coin, it's much more involved. It's like a gigantic, like was it 3,600 or something for 6 directions? I forgot. Yeah, it was a shame that I can't really save my old whiteboards on this thing. I'm not signing up for any nonsense, but like, well, I guess it's on me. But anyways, I can always rewind and look at the past stream to like to see what I did. But anyways, I keep like sticking bumper coins, but I should focus on Connect 4. Okay, so then 2 outputs. Yes, this is the 10H, I believe, that bounds you from -1 to 1. We could also use a sigmoid from 0 to 1, treat 0.5 as a draw instead of 0, but I mean, I'll just go with 10H, I believe. From perspective of the current player in a policy, that's a probability vector over all possible actions. When training the network, at the end of each game of self-play, neural networks provided training examples of the form, the state, the policy, and then the value, where pi is the exact estimate of policy from the state. We'll get to how pi arrives in the next session. Yes, using Monte Carlo tree search to like do them like to refine it. And then Z, which is like what the neural network thinks is, or Z is just like, yes, the final outcome of the game from the perspective of the player S of T. So like +1 means that the current player won, and then -1 if it loses. Like instead of P1, P2, from the neural network's perspective, like it does not know like what a player 1 is, what a player 2 is. This 1 and 2 are purely client side, like just like the game side. Like the actual neural network, it only thinks about things in terms of like the inputs is just 2 planes, and like if you swap the planes, like that kind of swaps the like it's just a current player whose turn it is to move, and the other player, like that's it. It does not know. It does not have a notion of player 1 or player 2. it just knows like current player and then the next one. So like the game state keeps track of like whose turn it is, player 1's turn, player 2's turn. But neural network, it does not care. Anyways, right. So back here, the neural network is trained to minimize the following loss function. So then there's like kind of like this and then that. When you log of a probability that's like less than 1, like between 0 and 1, then that gives you a negative number, so negative cancels out, so that makes sense, I think. So this stuff is simple, like kind of like the least squares, like this squared, like the mean square error. Yeah, this is just this is a bit familiar to me. This is just like sum over t, where t I'm guessing is the training sample. So what does t stand for here? Yeah, the training example, the form S of t, pi of t, z of t. So I think like the subscript t is for training. Yeah, state S of t. Final outcome, and then so neural network is trying to minimize this loss function. So we're summing over all the training examples. So then v of S of t is S of t is what the network spits out. Like it's what it predicts as the value, and z of t is from the training data, right? The training example of form this, where z of t is like, it's kind of like what the network thinks is the truth. Like it's what we're training on. And again, like this could be wrong, but like the more and more we like do Monte Carlo tree search and the more we iterate, like the more refined these samples would be. It's like kind of bootstrapping off of itself, like recursive loop. Somehow like magically getting better each time. But anyways, so this is like the value, like this is the loss from the value, like how much we deviate, and this is kind of the loss from the policy. Underlying ideas over time, network will learn what states eventually lead to wins or losses. Exactly what I was just saying. In addition, learning policy would give a good estimate of what action is best from a given state. So like I know like in the AlphaGo and like the chess and shogi, like the chess thing, even without Monte Carlo tree search, just just purely like if our output is a neural network and like we're only using neural network to play, like we're not even running, like when we're actually like playing the live game in production, like against other players, humans, like it scored like a pretty solid master level rating. I think was it like 2400 or something, like really strong elo. Anyways, so then the learning policy would get a good estimate for the best. So like not only do we have a neural network, which gives us like a strong neural network, which will give us like good predictions, like good policies to move, but like we can kind of run the tree search and like get it even more refined policy. Anyways, so I just read this sentence here. The neural network architecture would depend on the game. Exactly. This is why I'm doing Connect 4 first, because it's a much easier game. Easier to like architecture, like less variables, less weights and biases, less parameters, right? Like parameterized by theta. Well, the magnitude of theta is much lower for Connect 4 than BumperCoins. Most board games can use a multi-layer CNN architecture. DeepMind uses residual blocks, each with 2 convolutional layers. I was able to get a 4-layer CNN network followed by a few feed-forward layers to work for 6x6 Othello. So 6x6 is a very tiny size, and Connect 4 is a, what, 6x7? 6x7, I think. Yes, 6x7. So then this is like, yeah, I think this should work. Okay, so now how do we architect this? In TensorFlow.js. Well, if this guy got it to work, I believe like somewhere in GitHub I was actually like, let me actually find some okay, tic-tac-toe. Oh, they have, wait, the last year there is a Connect 4. Okay, so I could look at that. Should I look at that though? Oh, this is tic-tac-toe. Tic-tac-toe is nice and simple. I kind of don't want to look at that because like, is that cheating? No, I mean I'll look at it. I mean, again, like it's not like we have like it's not like we have a folder for BumperCoins. So yeah, what is Santorini? It's not like anyways. Go. Interesting. Anyway, I used to play dots and boxes when I was a kid. Anyway, so Connect 4. Connect 4 game.py logic players test. Yeah. This is what I need. The neural network and that. Wait, what's the difference? Okay, let's look at this init file. So this is about. Okay, so this is an empty file. Very cool. So this is what I probably need. Huh? Okay, again, all this stuff's in Python, whereas I'm using JS. And net wrapper. So it takes in the neural net. From neural net, import neural net. What is this neural net? Wait, is that the other file? Connect for neural net? Anyways, let's still look at this nnet stuff. So in it, I actually have not worked in Python in like a long time, like maybe like 5 years or more. So I don't really even, I don't know. OnNet, what is OnNet? From connect4.net import as OnNet. Connect4.net. Okay, so connect4.net is this file here. Residual blocks. Okay, so this is definitely what I need. Policy head. Yes, here's the actual like model. Residual. I don't want to do residual blocks. I don't. To be honest, I don't like really know how that stuff. I haven't really looked too much into it. So I want a very simple thing. This might be a bit too advanced for me, to be honest. Yes, I don't want to think about that stuff. Okay. I know. Yeah, no. Yeah, that's why I didn't want to look at Connect 4, because it's using like architecture that's kind of that I don't want to like really do. I want to use a very simple toy example. Yeah, Othello. Yeah, exactly. So that's the game I have to look at. Okay, let's just close these two files. But at least now I kind of know the architect. I mean, the structure of this folders. So then you have to click that, and then this is what I need. I think that one will probably be the exact same file, right? Yes, it takes in the. It takes in. Wait, what is it taking? OnNet. Search that. Okay, so yeah, again, I care about this file right here. It's a 6x6 game. Nice. So this is a very simple model, like 32 lines, 22 lines, about 20 lines long, maybe even less, from 13 to 32. Yep, and then if you can see here, the loss function, there's categorical cross entropy, and that is like this stuff right here is the category, like the entropy stuff, like the log probability, like policy stuff, and then this mean squared error, again, I mentioned that earlier, is a square of the error, and then mean because we're considering all the training samples. Okay, so let's see this. Game.get board size. Okay, so Othello is 6x6, so we just know that board X, board Y are 6x6. Okay. Self.action size. I actually don't know like I don't know how Othello is played, to be honest. But I'm assuming action size is like how many actions you can make. Then self. Okay. Self.input boards, input shape, board.x, board.y. Okay, so then this comment says S, I'm assuming a shape, is the bat size times board by board X by board Y, where like these X's are just like the like by, like row by column, like that. So then the image is I don't, why is this pop? Okay, so reshape board X board Y 1. Don't know where reshape is defined, to be honest. Is that like TensorFlow maybe? Yeah, actuation, I guess that's from TensorFlow. So then, for a bunch of these convolutional layers, ReLU activation, batch normalization, axis 3, num channels 3. So I guess 3 is probably the filter size. Like 3x3 filters are like very they show up everywhere, I think. So args.num channels. Guessing num channels is like kind of like 2, because like player 1, player 2 maybe. Channels. So they have 3 convolutional layers, and then they flatten everything, and then drop out. Okay. What does FC1, FC2 do? Oh yeah, it's just another layer. Okay. So like a bunch of convolutional layers, then they flatten it out, and then they add like some dense stuff, a few dense layers. Because again, like if all of these like convolution, everything were just dense layers, like then like there'd be way too many. Like that's kind of why like I'm not. I'm gonna be honest. I don't know why like I'm sure there are many more intricacies to convolutional layers, but like if everything were dense, then like there'd be way too many connections, right? Whereas kind of having like convolutional filters, you can kind of like use those filters and kind of like convolve like all the images, and like you can recycle those filters like so that like something like equivariant, like some like invariants or something about like how like you can kind of like translate, like basically it's like it's not like super dense, like all these dense layers which are like quadratic in terms of everything is like you need I mean, I guess the point is like it makes it like more it makes it more tractable. Anyways, so you have a bunch of convolutional layers, then you have flatten, then you have dropout, then you have so you have some dense layers here, and then here's why we can't use sequential, because you have like these two things right there, where like you have self.pi, self.v, where it's like that's the probability, that's the policy, that's the value. So that's the tanh from -1 to 1, and then this is the softmax. So softmax, is that like making sure it sums to 1, I think. Okay. Okay, so that's how it does it. And then that's okay, so this is the Python version. That's nice. Now I need to see a TensorFlow example. So let's go back here. Getting started TensorFlow.js. Recognize handwritten digits with CNNs fit. I think this sounds good. Getting started. Learn from existing TensorFlow.js code. TFJS. I think this is what I should look at actually. Okay, lots of folders. Okay, task type. I'm gonna search for CNN. MNIST transfer CNN. What else? Okay, that's it. MNIST image convolutional neural network. Okay, this looks good. Let's click that. MNIST. This example should you train MNIST using layers API. Tutorial examples here. Oh, what do you know? It's the same link, isn't it? This example live. Nope, that looks boring. Us data, I don't care about that file. Index.js. I think this must be it. Finally, create con model. That's what I care about. Create a sequential neural network. Okay, stop popping up. Network model, sequential. Okay. Input shape, image H, image Y. I mean, image H, image W1. So height is basically rows, and then width is the columns, and 1 is the color, the channel. Oh, so it's different from the other one, right? It's different from this where the channels were first. Whatever. I'll just go with whatever's the official example here. So I should have to use the restroom right now. Right. Okay. So first layer plays a dual role. It's both the input layer. It's both the input layer of the neural network and the layer that performs the first convolutional operation. It receives the 28 by 28, so I'm guessing that's H and W here. Pixel of black and white images. So black and white, that's exactly why this is 1. The input used 16 filters with a kernel size of 5 pixels each. Wait, what? But it literally says 3. Okay. A simple ReLU activation function. Okay, sure, I'll take it. After first layer, we include a max. Okay, I don't really care for max pooling because I don't remember what it does. To be honest, I'll just skip that out. Our third layer is another convolutional, this time with 32 filters. 332 ReLU, max pooling again. Nope, forget that. Add another conv 2D layer. Now we flatten the output. And then we add layers dense 64. Okay, so it's a dense layer after flattening pipes to dense. And then 0 to 9, where 10 is kind of, yeah, the probability distribution over 10, and then we softmax sum them to 1. okay, here's a super simplistic thing where it just uses only dense only. In fact, I could actually do that for Connect 4, just make it all dense. Like no need for convolutional layer, because it's such like a tiny example. Model criteria is approximately same number of parameters as create conv model, which I just looked at right now. Create conv model. Oh, that's cool. This thing gets sticky there. Yeah, exactly. Like I was just saying, like if we just have only 2 dense layers, like just 2 dense layers, like, and we can have like so many extra, like we can have like a convolutional layer here, convolutional layer. We can have like 3 convolutional layers and like 1 more dense layer. Well, 1 or 2 dense. I mean, the point is that like just with so few dense layers, like we incur like so many number of weights, like parameters. But it is expected to have significantly worse accuracy after training due to the fact that it doesn't utilize spatial information as the ComNet does. So it's like kind of not as good. I mean, it's nice and simple. Just like 5 lines of code. 1, 2, 3, 4, 5. Quite nice. Okay. Right. Okay. Now, how do I like not use sequential, but like use what they're doing here? I think it's called functional, right? Where like you have pi and like you have like 2 outputs. Like you kind of have to like each time you have a layer, you pass that into parameter. Let me just search that. TF.js functional versus sequential. No, but this is a Python. I want JS. Let me just duplicate, or let me just duplicate this tab and then go back to getting started with TensorFlow.js. More ways to get started. TensorFlow.js guide. Train models or models and layers. Ah, here we go. Functional model. Perfect. This is what I need to use. Model.summary. Okay. Well, I guess I'm using layers API, not core API. This seems a bit too low level for more. I'd rather have more abstractions. Okay, should I begin then? Should we let's start connect 4 ls get status. Let me just do get add all. Actually no wait. Get let's just do less of test.ts. What is this? Right, okay, so this one test.html is like kind of running TensorFlow.js on the browser, and then .ts is like, this is what I did last time. I had to like use Node GPU on this one. Okay, let's queue out of there. Okay, get status. Just do get add all status, and just a git commit. This is like, I could have actually done this last time, but we just call that what should my commit message be? Let's do a git log, see what my past ones were. Okay, git commit dash m test to test TensorFlow.js running in console and in browser status git push. Again, this has nothing to connect for, like the game. It's just like, it's just this thing right here, TensorFlow.js example, just to show that we can run it, right? Yeah. Okay. All right. So now let's just remove all the .js files. They're kind of annoying me. Oh, oops! Did I just? Oops. Whatever. Oh, okay. Oh, yeah, because my git ignore, right? Because I only care about TS files. I don't care about JS files. Okay. Git status. Let's just clear everything. Do an ls. Okay. So now let me just copy test.ts into connect for neural net, or just call it net, like for neural network, net.ts. Get status. Okay, now let's just actually work on net. So this is right. Okay. All right. Let's do this now. So we're using the functional API input. Input shape. Let's copy this. Okay. So yeah, I opened the other file so I can use the static, right? These num rows, num columns. Game.ts. Next. Okay. Let's go back to that one. Let's paste that here. So we're going to import game state. So what is the shape? Okay, actually I can look at the MNIST example for dense. So then the input shape is image H, image W, and 1, right? So in this case it would be 2. This would be, so the image H, right, the image height, like the number of rows, So I'm putting 2 here, for number of rows, num rows, num columns, and 2, because again, like I was mentioning here, like 2, the channel size, right? 2. Okay, so that's our input shape. I believe that looks good. Then what? What's the next? Oops, why did I close that? The next thing to do is dense one. tf.layers.dense dot apply. No, but we want this to be tf.layers.conv, right? Sensors and operations. Or like what I want to do is I want to like see like tf.layers.conv. I can look here. All right, okay. tf.layers.conv of this. Something like that, right? I guess I should look at the first one because that actually takes in the input shape, right? Sorry about that. I seem to have forgotten how to use Wim. The apply input, right? Save that. Okay, so then we're doing, and let's just call this conv1, like dense one, conv1, right? Like dot apply to kind of connect it. Okay, so then the kernel size is 3, the filter's 16. I don't know, let's just make it like 4. Actually, I can look at the example that this uses. Conv1, num channels 3. I don't really know what padding and use bias mean, to be honest. What is rx.num channels? I think that we find it probably here, right? Yeah, num channels is 512. 512. I mean, the thing is, I can just click model.summary and like kind of look at the parameter size. I want to keep it small. Okay, for now, let's just have it be some power of 2 as is tradition. 4. Or let's just do 8. Let's do 8 filters, right? Let's do 8. Okay, so that's one convolutional layer, and then we can kind of copy that here and then do another one, right? But now we do it in terms of conv2, right? And let's just add another one for good measure, right? Conv3. Sorry, R1. Something like this maybe? let's look at the MNIST example again. Conv. Okay, now I have to flatten it. So then tf.layers.flatten, right? Let's just copy that. tf.layers.flatten. So let's just call this conv flat or flatten. tf.layers.flatten, and then oh, sorry. What am I doing? What am I doing? Flatten dot apply on conv of 3, the previous layer, and that's flat. Let's save that. And then it just adds some dense layers. Okay, that I can probably copy from here directly. Dense what? Okay, so now 32, that's a power of 2. Now recall that like our output policy vector is going to be of size like 7 because we can drop it in any of the 7 columns, right? So it's like whatever like this number 32, it just has to be greater than 7, or it cannot be less than 7. It has to be greater because from then on we're going to have like kind of like our policy output would be like the of like game state dot num columns, right? So something like this, maybe like that. Let's make this a power of 8. 32. Let's make it like 16. Let's add one dense layer there. Like we flatten it and we add like kind of like our hidden dense layer, and then that's our kind of our value output. Our value output is units 1, just one value in the activate. To apply if dense 1. So something like this maybe. Outputs. The inputs are input, the outputs are like it's like both policy and value. Oh. So how do I specify? Because like right here we're specifying like it'll be dense 2. Okay, I need to see some like docs. API. Us. Okay, tf.model. It's a layers model, right? We're using a layers API. Dot, what was the method name? Just the constructor itself. Wait, dot model? tf.model, right? So the output is an array. It's like a tensor or an array of it. Okay, yeah, that seems fair enough. So then here, what we do here, the input, so the output instead of distance 2 is a list, right? An array of sorry, a list of this one, this guy, and that guy right there. Does that look correct? I don't know about like the loss functions and stuff. Activation softmax. Alright, 10H and softmax, right? Let's copy that there. Softmax, and then for this one it would be 10H. Let's just review the Othello one. And this Python. Get rid of this thing. Yeah, so the pi is a softmax, and then the value is 10H. Okay, so they have an extra dense layer, but I don't care about that. Input, yeah, outputs is a list of self.py v, correct? Model.compile. Okay, they're compiling it. Okay, compile. Let's do that. Model compile. Compile. Actually, first let me look at the model summary, right? I first want to look at the summary of the model. Okay. Call model.summary. Model.summary. Okay. Okay, so then how does this look right here? Is this just our do we have a model? I don't know. Let's see. Net.ts. Cannot find game state. Oh, right. So I just cast it. Okay. And same thing there, probably. Because, like, if you look at, like, if you look at this one, then, like, that one there, let's check it.